Hello and welcome to Math 275 Differential Equations here at Cañada College. My name is Lapuz, and in this video we will do an example problem where we have a Cauchy-Euler differential equation. It's second order and it's homogeneous, and we have a couple of initial conditions that makes this an initial value problem. So we begin by solving for the general solution, and we have our Cauchy-Euler second order homogeneous differential equation here. And remember that in order to do this, we want our solution to look like x to the m power. We take a couple of derivatives and put this into our differential equation. And then we can see after we put this in that each of the terms will have an x to the m in it. So we have an x squared times y double prime, which is going to be m times m minus 1 x to the m minus 2, minus 5x times y prime, which is going to be m x to the m minus 1, plus 8 times y, which is just x to the m. Again, each term will have an x to the m, so all we would have left for the first term is m times m minus 1, and then for the second term we have a 5m, and then for the last term just an 8. So we have a quadratic. These are all equal to 0. M squared minus m minus 5m plus 8 equals 0, or m minus 6m plus 8 equals 0. If we can factor, great. If we need to, we can use the quadratic formula. Two terms that multiply to 8 would be 2 and 4. Negative 2, negative 4, that would add up to negative 6, so I think this is factorable. We have a minus 2 and a minus 4 that multiply to positive 8 and add to negative 6. So our solutions, y1 will be x to the second power, and y2 will be x to the fourth power. That's m is equal to 2. And m is equal to 4. Okay, now that we have that, we can begin our process for solving for our initial value problem. We know that our general solution is of the form y is equal to c1 times y1, so that's x squared, plus c2 times y2, that's x to the fourth. And we want to use the initial conditions to solve for this. We also will need the derivative, so let's go ahead and take the derivative, and that will be 2c1 x to the first plus 4c2 x to the third. Now, using the initial conditions for the original function, when x is equal to 2, y is going to equal to 32. So this is going to be c1 times 2 squared plus c2 times 2 to the fourth will equal to 32. So let's say that this is equal to, or this is equivalent to 4 c1, and 2 times 2 is 16. C2 is equal to 32. That's our first equation. And in our derivative, again, putting x is equal to 2 in there, we're going to get 2c1 times 2 plus 4c2 times 2 to the third. And that should equal to 0. And that will give us a 4c1. This is going to be 8 times 4 is 32. c2 is equal to 0. All right, I was thinking about dividing out a 4, but I think we can work with this, and we can just subtract one from the other, so the C1s would cancel. And then this will give us a negative 16. C2 is equal to 32. So C2 will be a negative 2. And then put that into either equation. This one has a 0, so put it in there. 4C1 plus 32 times negative 2 is equal to 0. So 4C1 minus 64, and bring it over to the other side, it'll be positive 64. And then we're going to get C2, or C1, to be 64 divided by that. So I believe that's going to be 1, 24 is going to be 6, so 16. And then there we have it. Our solution would be essentially this thing, except we know what C1 and C2 are. So y is equal to 16x squared minus 2 x to the 4th. Okay, there you have it. That is your solution to our homogeneous second order Cauchy-Euler initial value problem. Okay, good luck.